we left off at the end of last class. And we'll finish up hypothesis testing. Maybe we'll get to confidence sets today. So remember, we were testing that theta is in some set versus that it's not. This is some subset here of the whole parameter space. And our likelihood ratio test looks at the likelihood maximized over the null, over the whole thing. And you could just reject when that's small and try to figure out where the rejection region is. Or if we're going to rely on the asymptotic approximation to figure out the cutoff value more easily, we just take minus 2 log that and reject when that's bigger than this chi-squared cutoff value. Remember that the degrees of freedom, which is one of the parameters of the chi-squared, is the difference in dimensions of these two sets. So that's an approximately easy way to do a likelihood ratio test. And so I want to start by doing an example of this. Any questions before I do the example? Okay, so this example is we're going to consider a multinomial problem. So we're going to have, as I call it, data. A 5-dimensional multinomial. So let's just to fix ideas here, let's say I take some people and I look at a gene in each person, and let's suppose this gene has 5 different versions. There's different, for example, for eyes, you could have blue, brown, green, whatever. This might be some blood type or something like that. So this will be the proportion of people in the population with the first version of the gene, the second, and up to, say, the fifth. And we're going to take a random sample from the population and count the number of people in each of the 5 categories. So that's a multinomial distribution, right? That's a multinomial. So we call that Y, which are the 5 counts. That's a multinomial. There'll be n people, and the probability that is data. Now, suppose you have some sort of theory about how these genes are distributed in the population, and your theory is that the first 3 groups are equally likely, and the last 2 are. In other words, your null hypothesis is that P1 is the same as P2 is the same as P3, and that P4 is equal to P5. And then the alternative is just that it's not. So not. So there's no obvious way to test this, or at least an easy way to test this with a wall test. As you can see, we have this high-dimensional or 5-dimensional parameter set, and the null is some subspace in this set. So first of all, we have to work out what the likelihood is. Remember, the likelihood, I don't know if I talked about the likelihood for a multinomial, but here it is. If we do the MLE, we have to be careful. If I just maximize the likelihood like that, we won't get the MLE. Why is that? If I just took the derivative, say equals 0, what's missing? Constraint. These have to sum to 1, these p's. So you need to do derivative plus, remember when you do constraint maximization, you have that Lagrangian and all that stuff in calculus. So that's a good exercise. That's a good question. Everybody's writing that down. But the MLE is not surprising. It's sort of what you think it would be. Where PJ hat is just Y-O-N. The trickier is, so let's write down the Lagrange version of this actually. So actually, the log likelihood looks like this. But you have to add a constraint. In this case, it's that the sum of the PJs. Right, that's how you put a constraint when you do a maximization, or one way to put a constraint is to add another term. because you can see when you take the derivative with respect to this extra parameter, instead of equal to 0, it forces the sum of the two bits to 0. So hopefully you remember that from calculus. How are we going to do the MLE under the null hypothesis, where we're going to add more constraints, right? We can add constraints for this, and it's not hard. There's a little bit of work to do, but it turns out what you get for the MLE, and this again is sort of you intuitively guess it, is under the null we know P1, P2, P3 have to be the same, so we end up with an MLE which satisfies that constraint. It turns out that I'll call it P1 0, the 0 meaning under the null hypothesis. But these are all equal, so they have to be, because we're doing it, we're maximizing under the constraint that they're equal. And these all turn out to be, if I did my calculation right, I'm not sure this is right now that I look at this. Let's see. I should check this, because I'm wondering if that should be divided by 3. Anyway, that's what I seem to have got, so you can check that. And P4, P5, and that turns out to be, they have to be equal, of course. So the restricted MLE is a little bit harder to compute. In a real problem, we're going to have to do a lot of these things numerically, of course, but we're doing simple enough problems that hopefully we can do them on the board. So now let's compute the likelihood ratio test. Well, first we have to compute the statistic. So it's minus 2 times log, and now it's P1, but on the top we have these null values. So P1, over the overall MLE. So I've just plugged in the maximizer into the null and the overall maximizer. Now let's figure out, we're going to reject this. So let's call this, as usual, minus 2 log lambda. We have to decide when to reject the null here. We reject H0 with minus 2 log lambda is bigger than a chi squared k alpha. But we've got to figure out what is k. It's the dimension of the full space minus the dimension of the null. What is the dimension of the full parameter space? Four. It's not 5, because once I've told you P1, P2, P3, and P4, you know P5. There's only 4 free parameters. Think of the dimensions as number of free parameters. So this is 4. What is the dimension of the null? It's a one-dimensional space. Once I tell you this, you know these two, and then it has to add up to 1, and these two have to be equal, so that's completely specified the thing. So if you think about it as a linear subspace, it's a linear subspace of dimension 1. And so the answer is 3. So k here is 3. So this is a good example of a type of hypothesis that actually comes up in practice, some sort of constraint on the multinomial. And it's not clear how you would test it otherwise. But here it's pretty simple. We just take the likelihood's pretty simple, maximize it under the null, maximize it under the alternative. And our rejection rule is if that's bigger than a chi squared alpha with 3 degrees of freedom, you reject, otherwise you don't reject. So it works out pretty simple. And that's a pretty good example of something you would want to use definitely a likelihood ratio test for. Any questions? All right. Now, there's one more test I have to show you. So we've done the Neyman-Pearson, wall, likelihood ratio. The last one is the permutation test. I mean, there's millions of other tests, right? But I think 4 is enough. Passes the desert island rule. I always ask, if you're shipwrecked on a desert island, what statistical stuff would you need to get by? I think if you have those 4 tests, you probably will survive on that. So you can stop with those 4 tests. But before we get to the last test, there's something I need to mention that I've wanted to wait till we've done a few of the tests, which is the notion of a p-value. Very confusing idea, but very common idea. Because the way I've been talking about testing so far is that you pick a level, like 0.05, you do your test, then you either reject or you don't reject. But in practice, people often don't want to pick, a specific level ahead of time. So they're looking for a way to summarize the test and without having to just choose a specific value of alpha. So the p-value, it's a random variable. Think of it as some sort of summary of the test. And here's the way to think about it. So there's actually two different ways to think about p-values. Let me show you the first way, which I think is actually better and clearer, which is, imagine making a diagram where I have alpha here. Now I'm going to ask, for any given value alpha, I can do a test at level alpha and say, will I reject the null hypothesis or not? So let's think about the normal example. Yeah, let's go back to the normal where I'm testing theta equals 0. Let's just say theta not equals to 0, just to have an example in mind. And what was the test? The test was to take root n, x bar bigger than this cutoff value. Where's that cutoff value? It's up here. Now, we think of setting the type 1 error at some level. If this is outside, so the rejection region is out here. And we've chosen that so that the probability of a mistake when the null is true is 5% or L, whatever alpha is. Now, if I made alpha more stringent, suppose I only wanted to make a 1% chance of making errors, well, what's going to happen is that number's going to get bigger, right? Because I want to make fewer mistakes. If I set alpha to be really small, like 0.0001, it's going to go way out here. It's going to be harder and harder to reject. So what I can do is I can ask for every value of alpha, would I reject or not? And of course, if alpha is tiny, the answer is no. Let's suppose my actual test statistic here was here. Then you can see if I made alpha really small, I would not reject the null. It's very hard to reject the null when alpha is 0.0001. But as I relax alpha and make it bigger and bigger and bigger, eventually I'll get to a point where I do reject. And of course, I'll keep rejecting after that point. So if I put here reject, don't reject, you can imagine making a diagram here that when alpha is really stringent, it's very hard to reject. So you're not going to reject down here, but there'll be some point where you finally reject, and you will reject for all alpha levels bigger than that. So this little chart is just showing you, if you're publishing a study, and everybody can have their own alpha level, right? You don't have to pick an alpha level, you can publish your study, and then other people can decide what alpha level they want to use, and they can look and see, okay, if my alpha level's here, I can't reject, but if I'm more liberal about making type of errors, I can reject. And you can see there's going to be a smallest point right here where you switch from rejecting to not rejecting. That's the p-value. The p-value is the smallest alpha at which you reject. P-value is equal to the smallest, let's say the minimum alpha, such that, and let's call the test, this would be a good notation here. I'm going to write phi alpha to be 1 or 0 to mean at the level alpha, I reject or don't reject. This is just this function I'm plotting. It's just saying at each alpha, do I reject or not? Depends on the test and on the data and so on. And so this is the minimum alpha such that, well, that's what the p-value is. And so people informally think of this as somehow a measure of the strength of this, of the evidence against the null. If the p-value is really, really, really small, you can reject it almost any level. That would say you should think of it as strong evidence against the null hypothesis. It's kind of a very informal thing. I think it's better to think of it as a summary of the behavior of this test on your data set. Now there's another way, let's go back to this. to think about the p-value, which is, remember that when alpha is out here, I can't reject. Here's my test statistic. It's out here, right? So if I keep asking for different alphas, when am I going to hit this point? It's going to hit the point right when my test statistic happens to equal the critical value. Right here. So let's suppose this is my test statistic. I'm going to try different alphas, and it's right here. When it gets to be right here, that's when I'm going to start rejecting. And an interesting thing happens. So that's this level of alpha, but it also happens to be the area over here. Right? That was the definition of the critical value, like say z sub alpha or whatever thing we're using, is we chose it to have probability alpha outside that region. So there's kind of a coincidence happening here. That the smallest, I start with a big alpha, I can't reject, I keep going until I can just reject. That's the definition of the p-value, this is p. But at that point, it also so happens that that p-value is this particular level of alpha that this happens to agree with. And when you're at that level, the null distribution, the amount of mass the null distribution puts into the rejection area is exactly equal to that particular alpha level. In other words, the p-value, to put that in symbols, the p-value can also be thought of as the probability. Well, in this case, let's call our test statistic z. If we imagine drawing a statistic from the null distribution, imagine taking a draw z from the null distribution. Okay, so let's call z a draw from the null. This is from 0. Then this is precisely the probability being bigger than this point. This is our observed test statistic. So this is, we'll call this z observed. Right, this is, I took the observed test, I took our observed value of the test statistic, I moved alpha until I got to this point where it just rejects. And this area by construction is alpha, where alpha is this particular value of alpha, the p-value. But that's simply the area in the rejection region under the null hypothesis. So it's as if I said, if I drew, just numerically, if I imagine drawing z from the null, maybe this is a draw from null. Let's even make this small just to emphasize it's our observed value. That this is called the tail area. It's the probability that a draw under the null is at least as big as our observed test statistic. So you might want to, if you haven't seen this before, you might want to run through this logic a few times on your own, because people describe the p-value in two different ways. One is they say the p-value is the probability that under the null you would get a test statistic at least as big as your observed statistic. I prefer to think of it this way. The p-value is just the smallest alpha which you can reject. It just so happens that that's equal to the probability that if I drew again from the null, that I would get a value bigger than my test statistic. And this is actually an easier way often to compute the p-value. And this is true not just for a z-test, but for any test that we've done. Every test that we've done, the p-value can be computed this way. It's the probability under the null. It's saying if I drew a test statistic from the null distribution, then what's the probability, I'll write it again, p0, to emphasize it's under the null, that t is just a general statistic, could be the absolute value of the walled statistic, whatever, is bigger than your actual observed value of your statistic. So this is what you actually computed from the data. This is a new draw from the null. And this is just a numerical fact, that if I compute this probability, it's the same as doing this diagram and finding the smallest level at which you would reject, so this is the p-value. So actually, let's continue with the normal case, because actually, let's do the walled test. So I test theta is equal to theta 0, theta not equal to theta 0. So what I'm saying is that the p-value, at least this is of course the asymptotic approximation of the p-value, is the probability, what's the distribution of the walled statistic under the null? It's standard normal. So it's the probability that a new draw from a standard normal is bigger than your observed test statistic, which I'll call, just call it the observed, where by that I just mean theta hat minus theta 0 over the standard error. This is the actual formula for the p-value. In fact, we can go further and say, by symmetry, this is the right side and the left side, so this is just 2 times the probability that z is less than this. Maybe to make it clearer, I can take it up, the absolute value off and put it here. It doesn't matter, right? And what is this? This is 2 times the normal density. So there's that's the p-value. I don't want you to confuse computing the p-value with the concept of the p-value. I think conceptually, I prefer this picture. If you get confused what the p-value is, just imagine trying your test, doing a hypothesis test for every value of alpha. You're just serving the community. There's different people with different alphas. You're going to tell them whether they can reject or not. The smallest alpha which you can reject, that's the p-value. But then you think, oh, how do I compute that numerically? It really just comes down to computing this. So you have a formula for the p-value. If we have a chi-squared here, we can do it for the likelihood ratio test and so on. In fact, let's do it for the likelihood ratio test. Under the null, the probability that minus 2 log lambda is bigger than or equal to our test statistic. So actually that's a bad way to do it. You should imagine that a fresh draw, all we're doing is we're taking the chi-squared distribution, we're taking our observed statistic and saying, for which alpha would we reject? Well, it's exactly when the critical value is here, and that's the same as computing this tail area probability under this null distribution. So that's the probability that a chi-squared with k degrees of freedom is bigger than your observed test statistic. That would be your p-value in that case. I know this can be a bit confusing if you haven't seen it before because we're describing the p-value one way, but we're computing it this way. But it's just because of the definition of what the p-value is, that it's exactly that value at which you would just reject. And that happens to be, we set that so that the tail area was exactly alpha. But these two things coincide. And you will see different textbooks define it in different ways. Some textbooks will define it this way, but I prefer to think of this as the definition, and these are the formulas used to compute the p-value. And a cool thing about the p-value, which I think you may prove in the homework, is that under the null hypothesis, this looks a lot like a CDF. In fact, it's just kind of like 1 minus the CDF. And what do we know about the CDF as a random variable? It's uniform. And so keep this in mind. The p-value is something that depends on your data. It's a random variable. And so a basic fact about the p-value is that when the null hypothesis is true, and you'll show this, p-value is a uniform 0-1 distribution. For the same reason that when you take a CDF of a random variable, as you saw, you know that has a uniform 0-1. Well, this is almost the same thing. It's just probably bigger than instead of less than. It's just like a CDF. So you'll do that calculation. So that's an interesting thing. In fact, you can recover your alpha level test because this has a uniform distribution under the null. And if you want to know, should I reject? Well, of course, that's just checking whether this is less than particular alpha. If I want to pick a particular alpha, but in other words, you reject the null hypothesis. Another way to say what you're doing is you reject the null hypothesis when the p-value is less than alpha. That's exactly the same as going back to the test statistic scale and saying I'm rejecting when my test statistic is bigger than the alpha level critical value. In some sense, we've really just done a change of scale of from the test statistic onto this probabilistic scale. Now, so this is the null, this is the distribution of the p-value under the null. The distribution of the alternative, really, it's hard to say what that is because it depends on what the true value happens to be. In general, it's something kind of, you expect small p-values if the alternative is true because you're going to be out in the tail of the distribution. So the distribution under the alternative is usually some weird distribution. It depends very much on the test statistic, on the test we're using and so on. it's going to be something kind of more piled up near zero. But the important thing is under the null hypothesis, the p-value, it's like getting a random draw from a uniform distribution. That's what it's like. So that's what a p-value is. Okay? Yeah.
Wait, can you explain again what's the intuition behind P being uniform under the null?
I think it's a homework question.
Oh, okay.
Is it? Is it? Yes. So you'll find out soon enough. But it's the probability of being out in a tail is kind of like 1 minus probability of being less than something, which is like a CDF. And we know that the CDF evaluated at a random variable is uniform. So it's just like when we showed that I think we did this somewhere in the course, that if x is drawn from a distribution f, then f of x is uniform 0, 1. It's really just the same fact. So it's essentially the same fact. Now what you have to be careful of, though, is there's so much misinterpretation of p-values. It is not equal to, the p-value should not be thought of as, it's not equal to, big not equal to, the probability that the null hypothesis is true, given the data. In fact, this doesn't even make sense so far from what we've done. The null hypothesis is not a random variable. You can't even make a probabilistic of it. Now when we talk about Bayesian inference, this will be a random variable, and we'll talk about what it means to compute this thing. But whatever it is, it's certainly not equal to the p-value. So you'll see people in the newspapers often get this wrong. P-value is 0.01. They'll say, therefore, the chance that the null is true is 0.01. No, that's not what it means. It just means that you could reject the test at level 0.01 and not small. That's all it's saying. So this is a really important conceptual thing. Another thing is, there's a lot of complaints these days, which I think are good complaints, that there's a temptation in certain branches of science to take people do the study, they spend all kinds of money in the study, do all this complicated stuff, and at the end they reduce it to some hypothesis test with a p-value. And people complain that that's really, first of all, it's just, there's so much information in your experiment, reducing it to this one thing, p-value, and is it less than 0.05 or not, is really not doing a good service to your community if you just reduce every study to just a simple thing of is the p-value small enough. But it's become kind of a problem because get small p-values, people like that, they reject the null, they get paper published, they get tenure, so there's a whole incentive system here to just reduce everything to a p-value. And then it also creates something called the file drawer problem, which is people do experiments, and if they get a small p-value, because usually they want to reject the null. So if they get a small p-value, they reject the null, and they publish the study. If they get a big p-value, they don't publish the study. And this creates a bias in the literature, because there could be 1,000 people doing the experiments. Most of them get huge p-values, but one guy, just by chance, after all, it's just like drawing random uniforms. By chance, somebody's going to get a small p-value, right? And so there's a very famous paper by an epidemiologist at Stanford, John Ioannidis. This is a great paper, look for it. It's called Most Published Studies Are Wrong, or something like that. It's a great paper, got a lot of press, and it's a very simple paper. He's just pointing out, basically, that, first of all, he's pointing out that people confuse this with this, and for this, to make this kind of statement, there has to be some notion of, first of all, probability on this, and then there's the whole issue about reporting bias and things like that. And so it is true that when you look at how often are studies that are significant, when they do follow-up studies, how often do they turn to be significant again? Not very often, although it varies from field to field. And it's because of all these biases and so on. So this has become a really important problem in science. And it varies a lot from field to field. For example, I've mentioned particle physics before because they're pretty careful about, you have to have a really, really, really small p-value before you reject the null. And even if you don't, then you can publish the study anyway because it's considered informative. So they're pretty careful about it, and it really depends on the field. But you'll read it, I'm sure you've come across things like this before in the press, or if not, you will notice it now because it comes up every now. All right, so that's a little bit of philosophizing about p-values. Let's get back to testing. Oh yeah.
So if we're just concerned with error rates, instead of setting a rejection unit for pre-zero alpha, choose p values for the rejection.
Well, because if you want to make sure you only reject 5% of the time, you're going to have to set alpha equals 105.
I mean, instead of zero alpha.
Oh, well, yeah, why not reject? That's a good question. Why don't I reject when p is between 0.5 and 0.05? Technically, that would have, you're right, that would have a 5% error rate, but you'd have a much lower power. So you want to be rejecting when the statistic is large, and that corresponds to rejecting when the p-value is small.
Doesn't that depend on what your alternative is?
It does, but it would be pretty weird to end up in a situation where you get more power by doing that. So you pretty much always reject when the p-value is small. Any other questions? Okay. Let's do our last test. Now, this test is one of the greatest inventions in statistics, I think. And unfortunately, it only can be used in certain situations. So I was tempted to skip it just because you can only use it in these pretty particular situations. But it's such a cool thing I have to do. And it's called the permutation test. It's just a very satisfying, clever idea. It can be used in certain situations of a particular type. The most common one is the two-sample test. So suppose I have two samples. X1 to xn is from some distribution f. And I have a second sample, y1 to ym from g. And suppose I want to test whether f and g are the same. So this would come up, for example, if I treat some patients with a placebo and with a drug. Is the drug doing anything, or is it the same as placebo? Or maybe you're a computer scientist, you're using a standard classifier, and you've invented a new classifier. Is it actually doing any better than this thing, or is it pretty much the same as the existing classifier, and so on? Anytime you might want to test that these two things are the same or not the same. So we're not just testing like necessarily whether the mean is different or not, just is f and g the same distribution or not. And so what we're going to do is take the data, and I'm going to, let's write it this way. I'm going to take the x's first, and then the y's, and I'm just going to call this whole vector z. So z has length. If I call this, z1, z2, so zn plus m. So this is of length zn plus m. I've just kind of strung them together. But I'm also going to create, I want to keep track of the labels. So we'll call that 1, 1, 1, 1, 2, 3, 2. Now, you can make up any test statistic in the universe you want, okay, to test these two things. Arbitrarily complicated. So, just to have a concrete example, let's make one up. Maybe it can be anything, but I'm gonna do the following. We talked about at some point the empirical CDF. That was quite a while ago, which was taking the data. You guys remember that? So if I have a sample, I can estimate the CDF by just counting observations. Right? So here's a sample. At any point, say x, I can just say what proportion of points are to the left. That's right. So that's 0, then 1 over n, 2 over n, 3 over n looks like this. So we talked about that a couple of times. And so, I don't know, here's an idea for a test statistic. I'm going to compute the empirical CDF of the x's, and I'm going to compute the empirical CDF of the y's. You can make up other things. You can be very creative here. So let me call that f hat of x and g. hat of x. I have two CDFs, and I'm going to take the maximum over x. That'll be my test. So if these two distributions are the same, I'm really estimating the same thing twice. Now what I want to do though is get a level alpha test. How am I going to make sure, under the no, I want to reject it 5% of the time? And here's the idea. You can think of this test statistic as some function of the z's and the labels. Right? You take, the test statistic says take all the ones with label 1, compute the CDF, take all the ones with label 2 and compute the CDF. So we can think of our test statistic as some function of all of the z's, all of the labels. Now here's what you do. You randomly permute the labels and recompute the test statistic. So you've sort of mushed up the groups, okay? And you compute the test statistic. Now here's the thing. Suppose the null hypothesis is true. Suppose the null hypothesis is true. Then these are all sampled from the same distribution. Commuting the labels doesn't change anything. It doesn't change the distribution of this statistic. Because there really is no group 1 and group 2. It's like somebody just randomly drew down some 1s and 2s. So this test statistic has the same distribution no matter how you permute the data. So every time you permute it, it's like you have a draw from the same distribution. So what you do is you create these permuted test statistics. I'll call that F, Z, and I'm going to call this, well, let's call it Phi, J, L. What I mean by that is you pick a random permutation and you permute the labels. That's what I mean by this. And recompute the test. And you do this, say, 1,000 times. It doesn't matter how many times, actually, but let's say 10,000 times. Let's say capital N times, to be a little bit more general. So what's going to happen is this. You're going to get, you have your original test statistic here. Now every time I do this permutation, I'm going to compute a new test statistic. I'm going to get a histogram of test statistics. A distribution of test statistics. And your test statistic under the null hypothesis has an equal chance of being the first one, second one, third one. The rank is going to be, there's no reason why it would be bigger or smaller if the null is true. Every permutation is equally likely. So in particular, I'm going to compute the number of these permuted guys that are bigger than yours. And the chance that that's 1 over n, that could be 1 over n, 2 over n, with equal probability. It's a uniform distribution. Actually, uniform discrete, but ignoring the discreteness is a uniform. It's a p-value. So the p-value is, you do this n times, and you just compute how often, this is the indicator, is the permuted test statistic bigger than your test statistic. And this is a p-value. This has a, under the null, this has a uniform distribution. Now there's one caveat, which is, you can see it's discrete for, with n is 10,000, it can only take values 1 over 10,000, 2 over 10,000. So it's actually uniform over a discrete set, not over the unit integral, but that's a small, that turns out not to affect anything really. So it's uniform on, I guess you could get 1 over n, 2 over n, up to 1, which we can think of as basically a uniform on 0, 1. So under the null hypothesis, we've got our p-value. You would reject the null if this p-value is less than 5% or whatever you want your error level. What makes this test great is, well, first of all, this is finite sample. There's no asymptotic approximations going on here. But what makes it especially useful is it doesn't matter how complicated this test statistic is. If I tried to figure out theoretically how to reject, I'd have to figure out what's the distribution of this test statistic under the null hypothesis. It could be a very complicated thing. And I have to say, in the last few years, there's been a renewed interest in this, what's called two-sample testing, in the high-dimensional situation. Imagine now we have, these are random vectors now, and they're very high-dimensional. Because these days, everybody's interested in high-dimensional statistical inference. So people have thought of very inventive tests for how do I test that two distributions are the same in the high-dimensional situation. And there's some fairly complicated, sophisticated tests people have come up with. But then they come up with a test statistic, and they always come to the same problem. How do I know when to reject or not? It could be something very complicated. Working out the distribution of a complicated test statistic under the null could be really, really hard. And the answer is, well, at least if you're willing to do some computing, just do a permutation test. And you're guaranteed to get the right size alpha test. Now, there is a computational cost, right? Because you're going to have to do this, say, 10,000 times, and every time you have to recompute your test statistic. So hopefully the test statistic doesn't take so long that it's impossible to do that. But assuming you can do the computation many times, this is like a guaranteed way to get a nice test. Right? So you can see that it's only useful in a certain situation. There's a few other cases where you can use similar reasoning, but it's not going to be a general test. It's really restricted to something like testing the two distributions are the same. There's a similar test for checking whether correlations, things are correlated and so on. But when you are in that situation, it is nice to know that there's this very simple, kind of very, very universal test. Now, one thing that you might wonder though is how can this work for any test statistic? Well, the answer is, we're just getting the type 1 error right. I'm not saying you're going to get good power. One test statistic might have better power than another test statistic. That's a whole other story. Trying to design a test statistic that has good power against the kind of alternatives you want to have power against could be itself, quite a bit of work. So I'm not talking about how to get good power here. I'm just saying once you've chosen a test statistic, this is how you can figure out when to reject them. And it's just solving that part of the problem. Okay, so I always feel like I should teach that because I think it's a pretty cool idea. And that completes everything we want to do about testing. Are there any questions about this or about anything else we talked about in testing? No questions. Okay, then we can keep going. Just saying I was going to keep going caused him to ask a question.
So this test that we're doing here doesn't depend on the test, on the actual statistics.
This procedure works for any test statistic, that's right.
So why would we choose one test over another?
Power.
Power?
Yes.
So the test that we choose gives the power to this other.
That's right. And so you and I can use two different test statistics, so we can use this permutation procedure, and we can both claim we're controlling the type 1 error rate at alpha. But your test might have more power than mine, and that depends on what kind of alternative you expect. So designing a test with good power, that's a whole other story. It's very problem specific. Okay, good. So now that we know about testing, I want you to forget about it. Because, as I've said, you really shouldn't do testing very often. I think it's overused. There are times when you want to test, there's no doubt about it. But I think most of the time we don't want tests. And on the other hand, we don't just want a point estimator either. Just saying theta hat's equal to 17.2 is not very informative. And that's where we get to the next topic, which is confidence sets. Confidence set is much more useful, generally speaking, than either a point estimator or a test. And as the name implies, it's a set. Not much of a surprise there. So the goal is this, is we get our data, and we get our sample. We're trying to estimate some parameter theta, let's say, so I'll estimate theta. And now what we're going to construct is a set C sub n, and actually, to write it out more fully, it's going to be a function for data. So this could be, when I say a set, it could be an interval in the real line, it could be a sphere, it could be an ellipsoid, it could be anything. But it's a set, and it depends on the data, so it's a random set. And what we want from a confidence interval is that this set traps the true value with some probability. So I want to make sure that the probability that, let's be really careful what this is saying. So again, I'm going to pick some number alpha, but common choice would be 0.05. And I have a model, don't forget, a set of distributions. And I want to say that no matter what the true distribution is, So whatever my model is, no matter what the true distribution is, the probability that theta falls in Cn is at least 95%. Now we have to be really careful when we look at the statement, because remember, this is not random. This is fixed. What's random is this part. Okay, so it's saying that the way to think about it is it's the procedure that's random. And the way I like to explain it is you write some software for computing this confidence set and you post it on your website. And now a million different people say, oh, I'm going to download this guy's software and use it to compute this confidence set. They all have a different theta. They all have a true theta. They don't know what it is. They compute this confidence set. Some of them, their confidence set will contain the true value, theta, and some won't. But you know 95% of them will contain the true value. It's the procedure or the confidence set that's the random thing. Okay, I knew a guy who used to teach this by, he would put a frisbee here, he would take a coin, and he'd throw the coin into the frisbee and go, no. And then he'd put the coin here, and then he'd throw the frisbee and say, yes. Because what he meant was the frisbee was the random set, and you're saying, how often is the random set going to trap the true value? Okay, so, now it might seem like a small distinction, but later when we talk about Bayesian inference, we'll see that when we do Bayesian inference, you're going to remember in Bayesian inference you treat theta as like a random variable, and we're going to compute sets of the form the probability that the probability that theta is in A, given the data is 1 minus alpha. And then we can say, okay, treating it as a random variable, I can actually make a probability statement with theta. Then we can ask, does it have this property, this confidence interval? And the answer is no. They're very different. And it's very hard to see the difference at first until later in the course when I show you specific examples where we're going to construct examples where the Bayesian probability that theta is in A is 95%, but the actual number of times if we repeated it, it contains the truth is like 0. So they can be very, very different. So we'll come to this later. Maybe we shouldn't think about it yet. We'll come to it later on. I don't want to confuse you. Looking ahead a little bit. Just keep in mind, this is random and this is fixed, and it's how often. If every one of you computes a confidence set, how often will you have victory that your confidence set traps the true value? And the important thing is, this has to be true, whatever the true distribution is. It can't depend on what the true distribution is, or it would sort of defeat the whole purpose. So in fact, another way to write this is, since this is true of every p in our model, another way to say this is, over all distributions in whatever model you're using, of this probability, that minimum has to be at least 1 minus alpha. That's really the hallmark of a confidence set. And we call this the coverage. How often does it cover the true value? So we've successfully constructed a confidence set if that coverage property is true. What we're going to do on Friday is start talking about different methods for constructing confidence sets. And here's the cool thing. One of the main methods, one of the most general methods, is to first construct a test. And then you can convert your hypothesis test into a confidence set. And that is the most useful thing about hypothesis tests. It's a way to construct confidence sets. Any questions before we disappear? All right. I will see you on Friday. All these statistics students in here, come to today's seminar at 4 o'clock. Very good seminar.